Last time I discussed a bit about how scientists view nature at molecular dimensions. One of the reasons scientists think that quantum mechanics is a complete theory of the microscopic is because it is capable of explaining all objective data. Well, as we'll see, not quite all. There is one experiment that causes trouble, but otherwise, with no evidence of anything deeper, how can we know if subquantum domains actually exist? The least we should expect from a physical theory is that it is consistent with the reality, completely explains all phenomena, and deterministically allows for events to be predicted from some initial cause. We should also expect interactions to be local. Quantum mechanics fails in all these. Particles are real, and we have many ways of determining and confirming the structure and function of molecules. That is chemistry. And interactions fall off with some inverse power law, so they're local. From a source, the intensity drops off the further you are away, like the light from a distant star. This is an example of an inverse power law, and all forces, well, there are only four, become weaker with separation until they are negligible and can be ignored. Evolution is deterministic. Here is an example of cause and effect. In our world, where classical mechanics is applicable, all processes are deterministic, but not in quantum mechanics. We'd also expect a physical theory to describe all properties of a system accurately. Quantum fails there too. Well, maybe these are not failures of quantum mechanics. Maybe quantum mechanics is complete and accurately reflects the way nature is. So maybe reality does change, and we can let philosophers argue about the ontological difficulties. Maybe nature is not deterministic and only gives probabilities, and God really does roll dice. But that is not very satisfying, as attested to by the large number of attempts to understand and interpret quantum mechanics. Right from the beginning, scientists have been troubled by these issues, yet wowed by the success of quantum mechanics. It started about the time of this famous photograph showing the participants of the 1927 Solvay conference in Brussels, which was chaired by the well-known grandfather of physics, Hendrik Lorentz. The focus on this conference was the interpretation of the wave function, and most were on the side of Niels Bohr, who believed quantum mechanics a complete theory, but with Louis de Broglie and Albert Einstein as notable exceptions. In his summary at the end of the conference, Lorentz expressed what has been echoed many times since: dissatisfaction with the rejection of determinism. Let's look at a chronological list of some of the many attempts to interpret quantum mechanics since that time. Consider all these: the ensemble interpretation, the famous Copenhagen interpretation of Niels Bohr, hydrodynamic, projective measure, quantum logic, Bohmian mechanics, many worlds, stochastic mechanics, many minds, statistical ensemble, consistent histories, objective collapse theories, transactional, rational, incomplete measurement. The list goes on longer than this. All accept quantum mechanics to be a complete description of nature, except the ensemble approaches and David Bohm's Bohmian subquantum mechanics. Notable here is the Copenhagen interpretation, which today is still perhaps one of the most accepted, and first articulated by Niels Bohr at the 1926 Como Conference in Italy. It too assumes completeness of quantum mechanics. Quite a few interpretations require the wave function collapses upon measurement. This is also called reduction of the wave function. I remember when I was taking a course in quantum physics as a graduate student at UBC. I was not really paying much attention when suddenly I heard the prof say, and the wave function collapses. He suddenly had my attention, and I had a strange image of quantum mechanics falling apart. But the more I looked at it, the less sense it made. I had no answers, of course, but it needled me from then on. There's a notable paper by Leslie Ballantyne. He explains the statistical interpretation of quantum mechanics and compares it to other approaches. In that paper, regarding the enormous numbers of papers on the theory of quantum measurement, Ballantyne states, "The reader can shorten his task greatly by ignoring all papers which try, without modifying quantum theory, to accommodate the reduction of the state vector, and which also assume the state vector to describe an individual system." So we can cross out the interpretations of quantum mechanics because only the statistical ensemble approach leaves open the door for a subquantum theory. All others maintain that quantum mechanics is a complete theory of the microscopic. So since we are discussing the possibility of subquantum theories, let's cross them out too. Only the statistical ensemble interpretations, as discussed in that paper by Ballantyne, allow for a subquantum theory to complete quantum mechanics with properties that satisfy local realism, causality, and determinism. That a suitable subquantum theory has not been found is a human failing, and nothing more. Now, I'm not including number 6, Bohmian mechanics, because it is a subquantum theory rather than an interpretation of quantum mechanics. Also, I'm not rejecting the other interpretations, but just noting that they all consider the quantum mechanics to be complete. So, to what systems is quantum mechanics applied? Since we can recover classical mechanics from quantum mechanics, we could move into the cosmos, but let's not go too far. Let's not consider the cosmos and questions of quantum gravity, black holes and dark matter, etc. The cosmos is big. Cosmologists estimate the number of stars in units of sextillions. How about our macroscopic surroundings? We know that quantum effects are manifested in many ways, but they are indirect. They are there, but you can safely ignore them without hindering your ability to function normally. In fact, from an empiricist point of view, we can only see microscopic effects indirectly, as numbers on meters and deflections of needles. Quantum mechanics becomes relevant when Planck's constant becomes important. Planck's constant is a very small number. He first discovered his constant while studying blackbody radiation in 1898. As you heat a black body, say by turning on your stove, it starts to glow and give out radiation. The intensity and color depend upon the temperature of the body. One of his critics, James Jeans, who tried unsuccessfully to use classical mechanics to describe blackbody radiation, and which led to the ultraviolet catastrophe, said, "The real value of Planck's constant is 0. In classical mechanics, he is right, but quantum mechanics describes phenomena where its value is non-negligible." This is where quantum starts to be relevant. Many people incorrectly think that Planck's constant is the smallest quantum of energy, but that is not correct. It has units of joule seconds, which is angular momentum. You can see that a joule is a kilogram meter squared per second squared times seconds, so a seconds cancel. Take out a meter, and that leaves position times kilogram meters per second, which is mass times velocity, or momentum. So the units of angular momentum are joule seconds, which are the units of Planck's constant. Likely the value of Planck's constant was fixed at the time of the Big Bang, and after that, along with other fundamental constants, our periodic table was set. But back to the fit of quantum mechanics in nature. Before I mentioned that the Heisenberg Uncertainty Relations have nothing to do with measurement, but they do put a limit on how we prepare a system for measurement. That preparation fails unless it satisfies the Heisenberg Uncertainty Relations. If preparation is impossible, then measurement is impossible. Quantum mechanics is a theory about measurement of the microscopic, and the Heisenberg Uncertainty Relations give a limit of its applicability. Let us call the microscopic domain that lies below the Heisenberg Uncertainty Relations the quantum noise. Is it only noise? That is uncertainty, dispersion, and random events? This is the subquantum domain. Here I do not mean quantum noise in an experimental sense, like shot noise. Quantum noise is defined here by the statistical nature of quantum mechanics as determined by the Heisenberg Uncertainty Relations. This gives us a big hint. If quantum mechanics is a theory of measurement, which is limited by the Heisenberg Uncertainty Relations, then we can surmise that one of the properties of a subquantum theory is that it cannot be directly measured. We can ignore the measurement problem in developing a subquantum theory. Quantum mechanics does the measurement job well, and even sets limits of its applicability. So what good is a subquantum theory if it cannot be measured? Well, just as quantum effects indirectly affect our macroscopic surroundings, so a subquantum theory can lead to measurable effects indirectly on quantum mechanics. In other words, unless something new emerges from a subquantum theory, then we might as well forget it. new predictions and results are needed, and these must agree and be consistent with quantum mechanics. This is one of the difficulties with Bohmian mechanics, an intriguing subquantum theory, but nothing new is predicted, so it cannot be confirmed. Here's a summary. Cosmology down to our classical Earth, and then into the quantum world where Planck's constant rules, and perhaps, finally, to an elusive, hidden variable subquantum mechanics that restores objective reality to nature and restores ontological sense to science. Of course, a complete unified theory is still the holy grail of physics. Perhaps some clues lie in finding something that lies below quantum mechanics. And if so, what? Well, the truth about reality would be nice. So in my next entry, I want to talk a bit about how objective reality at microscopic dimensions differs from that of our macroscopic surroundings.